We're now going to talk about the composition of functions, and I have the definition here. This is an operation on two functions, two or more functions, that when you compose them, you're going to get a third function here, and it's defined in this way. So if f and g are functions, f compose g of x is really equal to f of g of x. Okay, and so the idea is you're basically taking x, putting it in g first, and then you're taking the answer to that, and then you're putting that into f to get the final answer. So if you wrote it like this, so you're taking x, you apply g to it, and you get g of x, then you apply f to g of x, and then you get f of g of x. And what you can do is do it all in one step by doing f compose g of x. Okay, so you do have to restrict the domain on these sometimes, because the domain of the composition are going to be all the values that are in the domain of g of x, such that g of x is actually in the domain of f of x. Okay, because you can't do an x here and then get a g of x that's not in this domain and have that still be in the domain of this, if that makes sense. Okay, so it's pretty easy to check that. And so let's do it. Let's do a couple here. You're just going to, basically you're going to compose them, and then you're just going to find the domain of the function, the resulting function. Okay, so let's do, I'm going to do f of g of x. These are my two functions. So this really means f of g of x. So what it means is that this g of x gets placed inside the f of x. Okay, so the g of x is the inside function, the f of x is the outside function. Okay, so the one closest to x, that's the inside function. It's kind of like you're starting here at x, you're putting it in g, and then you're putting that in f. And so the g is the inside function, the f is the outside function. So g is inside of f. And it's going to be important to be able to distinguish what's the inside function and what's the outside function, because we're going to learn a rule called the chain rule, and it's a shortcut rule for differentiating the composition of two functions. And you got to know which one's inside, which one's outside. Okay, so what about the domain of this? Well, basically, just look at this original, or just look at the final function. Well, I have to restrict the domain so that there is no negative number underneath the radical. So basically, 2x minus 1 has to be greater than or equal to 0, which means 2x has to be greater than or equal to 1, and that means x has to be greater than or equal to 1/2. So the domain here would be, it could be equal to 1/2, or anything larger than that. So 1/2 up to infinity. This would be the domain. And I'm not worried about the range here, but the range would be 0 to infinity in this case. And on this assignment, it's just asking you to find the domain. Okay? So now we can compose it the other way. I could do g of f of x, right? We could do this too. So this just means put f of x inside g of x. So now the inside function is the f of x, the outside function is the g of x. So this is the inside function. I'm placing that in for x here, so it's like you're erasing that x and you're putting this in its place, which would look like this, 2 square root of x minus 1. And in this case, the domain here is just going to be 0 to infinity. The only problem is you can't have a negative underneath the radical. So that would be the domain. Okay, and notice that you do not get the same thing. Okay, so the composition of functions is not normally equal to the same thing. So its composition is not commutative. F compose G is not the same as G compose F. Okay, there's a couple functions where it is, but not normally. So let's check out this example. Let's do f compose g of x. Okay, and then we're gonna put x inside of g and put g of x inside of f of x. So it's really f of g of x. Okay, so this is the inside function, and I'm putting that inside here. So I'm going to get 1 over x squared minus 4. Okay, so this is the composition. You can think of this as the composition of 1 over x, that's the outside function, and inside that, you can almost think of f of x as just being 1 over something. And then inside that, I'm putting x squared minus 4, right? So this is the inside function. 1 over x is the outside function. Okay, well, what about the domain here? So basically, you can't have a 0 in the denominator here. So I got to restrict the domain. So x squared minus 4 cannot equal 0, right? So basically, I just find out when it is equal to 0. Well, this thing can be factored like this. Okay, so this times this is equal to 0, and so it's equal to 0 when x is equal to 2, or when x is equal to negative 2, or when x is equal to positive 2. And so basically, all real numbers will work here except for these two. So the domain, I can do negative infinity to negative 2, and it doesn't include that negative 2. Negative 2 to positive 2 doesn't include the positive 2. And then 2 to infinity. So that's how I would write the domain for that in interval notation. Okay, well, let's try the other composition, right? G of f of x. This would be like g of f of x, right? So now I'm putting f of x into here, right? So in for this, I'm like taking out the x and putting that in. So I'd get like 1 over x quantity squared, okay, minus 4. Okay, I could probably simplify that to just 1 over x squared minus 4. You could combine it over common denominator, whatever. This is fine. And to get from here to here, of course, I just squared numerator, squared denominator. Okay, and so now what about the domain here? Basically, you can't have a 0 in the denominator, but it can be negative. That's not a problem. So it's negative infinity to 0 and 0 to infinity. Okay, so what I got here are some compositions. Okay, and so I want to recognize like what are inside functions, what are outside functions. And there's more than one way to do this. Okay, so let's actually break this up in several different ways. So for example, like this one here, I could have like my outside function, we'll let f of x be the very outside function, and I could have that be 1 over x, and I could have my g of x be x squared minus 1. And that way, if I do f of g of x, that would be f of g of x, and I'm placing g of x inside there, I would get 1 over x squared minus 1. So this could be my outside function, right? That whole thing, and that could be my inside function. But I could also do it like this. I could do, let's say f of x is equal to 1 over the square root of x, maybe, like that. And g of x would be equal to just x squared minus 1. And now this is my inside function, and it's going inside the f of x, right? F of g of x, which is f of g of x. And that would equal, you're putting this inside that x there. It would be the same thing. So there's multiple ways. There's not necessarily just one way of decomposing a function. Another way here is I could actually get 3 different functions, right? I could let my f of x equal 1 over x. Then I could have my g of x be the square root of x. And then I could have my h of x be x squared minus 1. And then, if I do f of g of h, right, which looks kind of bizarre, but if you combine it all, you're putting, you'd have the x here. What you would be doing is you'd be putting x inside of h, and that inside of g, and that inside of f. So let's see if I can do this. F of g of h of x. Something like that, right? And so then you're putting this inside of there, and you're putting that whole thing inside of there. And you would get, okay? So clearly there's more than one way to skin a cat, or whatever. I shouldn't say that. There's more than one way to decompose this thing. Okay. Well, what about this one here? Well, we could do similar things, right? One thing that's interesting is I could rewrite this as 2 over x quantity squared plus 3, right? And then if I did that, then I could rewrite this in several different ways. I could do something just like if I had it like this, I could have my f of x, my outside function, just be the square root of x squared plus 3. And then my g of x could be 2 over x, something like that. Then I have f of g, right, of x, and that would be f of g of x, okay, and that would be placing this inside there, which would be like this, which would equal 4x squared if I square the top and bottom. So that would be like one way of doing it. But I mean, it's not the only way of doing it, right? I could do f of x be the square root of x, g of x then would be x squared plus 3, and h of x would equal 2 over x. Okay? And then I'd be putting this inside there, so I'd have f of g of h of x, right? And that would end up giving me the same thing. I mean, so you can break it down in different ways. Okay? So now let me finish with one last topic, and I don't think there's really anything like this in the homework, but I just think it's important, and it's related to the composition. And basically, a way of defining inverse functions are just two functions. We'll call one f of x and the other f inverse of x, a little minus 1 exponent. And these are said to be inverses if you compose f inverse, and that's equal to f inverse compose f, and that's equal to x. So in other words, two functions are inverses of each other if they undo each other. So if I put x in f inverse and put that in f, and I get x back out, or if I put x into f, and then I put all that into f inverse, and I get x back out. It undoes. They undo each other. Notice in this case, the two functions actually are commutative, okay? And they undo each other, and you're left with just x. So what I want to do is I want to show you how I can find the inverse. We're going to find the inverse of that function. Let me show you how that works, and then let me show you what happens when you compose the two. Okay, so the way that you find the inverse is I'm going to say y is equal to f minus 2x plus 3 squared. And what I'm going to do is the inverse, basically, the inverse function has the x and the y's switched around. So in other words, if I put in x and I get out y, then if I put y in the inverse, I'm going to get out x. And so if I switch the x and the y around like this, and then I solve for y here, then I'm going to get the inverse, okay? So this would be like x minus 5 is equal to negative 2, y plus 3 squared, and then I'm going to bring the negative 2 over to the other side, and if I do that, I'm going to get x minus 5 over negative 2 is equal to y plus 3 squared. Now what I can do is I can get rid of that negative by commuting the top. So x minus 5 is equal to the opposite of 5 minus x. And I just think that looks nicer. And this is equal to y plus 3 squared. Now I'm going to take plus or minus the square root of both sides. Now notice this is a parabola, okay? And if I invert that, I'm going to get a parabola on its side, which is not a function. And so I'm going to need to decide, do I want the positive one or the negative one? So if you don't state it, then it assumes you're taking the positive root. They call that the principal square root. So I'm going to just take the positive one here. And so then what I'm going to get over here, this is just left with y plus 3 is equal to, and this will be the square root of 5 minus x over 2. And then I can move the 3 to the other side. Minus 3. So it would look like that. And so f inverse of x would just be the square root of 5 minus x over 2, all that minus 3. Okay, so that's the inverse function. And so now let me show you that compose f inverse of x is going to be equal to 0. So what this means is I'm going to be putting x into this, and I'm going to be putting all that into this. So this gets big and messy, but it's not too bad. So that's in for x, and then I have that plus 3, and then it's squared. So all of this is in for x. The inverse is being plugged in for x. Okay? And so the 3's cancel out, right? And I'm left with this. And then the square undoes that square root, so I'm left with this. And then these 2's cancel out, and I'm left with 5 minus 5. And this thing should be like a parentheses minus x. So I can distribute that parentheses, 5 minus 5 plus x, right? And then these cancel each other out, and I'm just left with x. So if I compose them, it undoes it, and I'm left with x. Maybe what I'll do is let you do this, if you want. You can compose them this way and show that that also equals x, because it doesn't matter which way you compose them. Okay? Now I have one more I thought I would do, just because this is some good algebra and things you need to be aware of. So this is a more complicated one, but we're going to find the inverse of this. Okay? And so I'm going to first do this. Okay, and then I'm going to switch the role of the x and the y around. So the y becomes x, and now both of these x's become y's. Right? And now I got to solve for y, and this can be a little tricky. In fact, I remember when I took pre-calc, I had one of these on the test, and I could not solve it. I could not get y by itself, and I kept going around in circles. It was the one problem I didn't get right on that first test in my pre-calc class. But now you can be sure I know how to do it now, right? So what I'm going to do is I'm going to bring this up to the other side, like this, and so I get this, and then I'm going to distribute the x, and I kept trying to get y by itself, so I'd move that over, divide by x, but I'd have a y over here. I'd go back and forth, and I couldn't do it. So here's what I was missing, is what I need to do is get all the y terms to one side and all the terms that don't have a y to the other side. And here's y. So I'm going to move this to that side and that to that side. So I get 4y minus 2y is equal to negative 3x minus 5. And the reason I do that is because now I can factor out a y. And that's what I was missing. Okay? So, so I'm factoring out, oh, here, I forgot to put this x. See that? There's an x there. So I'm going to factor out that y, and it's going to leave me with 4x minus 2. So if I redistributed it, I would get this, right? And then negative 3x minus 5. And then I can just divide both sides by the 4x minus 2, and I get this. Okay, so my f inverse of x is equal to negative 3x minus 5, 4x minus 2. Okay, so that's some nice algebra, especially this little trick of getting everything with the y term to one side, factoring out the y, dividing both sides to get y by itself. Okay, and another good, this is good algebra practice, is composing these two and showing that they cancel out. Okay, so let's actually try that. So if I compose these two, it means I'm putting this in for each of those x's. Does that make sense? So let me write this as f inverse of x. And now, give myself some room. This would be 2, and then in for x, I'm going to put in all of the f inverse. And so it looks really complicated. But you know, when the math gets more involved, like in a calculus class, it gets really, you got to be able to plow through it. So you need to be able to write things out, each thing equal to the next, to the next, to the next, until you get the right answer. Okay? So now I'm going to put this in here, and so I get negative 3x minus 5 over 4x minus 2, and all that plus 3. Okay, so now what I need to do is I need to combine these over a common denominator. Okay, so I'm going to first distribute the 2. So negative 6x minus 5 over, or minus 10, sorry, over 4x minus 2, all that minus 5. And then I'm going to distribute the 4 over. This is like multiplying the top and bottom. And so I get negative 12x minus 20 over 4x minus 2. That is going to be all that plus 3. Okay, now put these over 1, and now I'm going to combine over a common denominator. So this will be this times this. So negative 6x minus 10, and that's a minus, so it'll be minus this times that. So that's like 5 times 4x minus 2, all over 4x minus 2. And all of this, now combine these over common denominator. That times that. Plus this times this. Okay, all over 4x minus 2. Okay, so now what I'm going to do is I'm going to invert this and multiply, okay, but then the 4x minus 2 is going to cancel out. So if I invert that, multiply, I'm going to get negative 6x minus 10, and I'm going to distribute that 5 over as well. Minus 20x plus 10, all over, And then this bottom will be negative 12x minus 20 plus 12x minus 6. Okay. Now, these 10s cancel out, right? And this 12x cancels out, the 12x's. And so what I'm left here, negative 6x minus 20x is negative 26x. And then negative 26 minus 6, or negative 20 minus 6 is negative 26. And these cancel out, leaving me with just x. So indeed, you compose them and they cancel out. So maybe what you can do, and this is good algebra practice, is compose them the other way and show that again it does cancel out. Okay? And notice every single thing is equal to the next thing. Okay? I'm not just kind of, putting a little scratch work. If I have to rewrite a whole bunch more, I'll just do that just so I have that step, and then I can go from that step when I make the next step. Okay? Now it doesn't mean I can't skip steps. Like when I went from here to here, I skipped quite a bit. I inverted it, I canceled things out, and I distributed that over. But all of that made sense to me. I knew exactly what I was doing. Okay? But the point is that all of this is equal to all of that, is equal to all of that, is equal to that. So what I'm given is, since each step is equal, this is equal to that, and that satisfies the definition. Well, half of the definition. And then if you show this, that would satisfy the other half. Okay? So, that's the composition of functions, and also a little bit with the inverse functions.